Welcome to Understand the Math. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch the video. This is the fourth part of a 7-part series on topics that commonly appear in an introductory linear algebra midterm or final exam. This video goes over the 4 topics of determinants that are listed here. We'll begin by learning how to calculate the determinant of a 2x2 matrix. The determinant of a matrix can be written as determinant A, or notated like this. You have a straight bar, and then you have the entries in your matrix, and then another straight bar on the right-hand side. The determinant is equal to the product of the entries along the main diagonal. So that's going to be A11, A22, minus the product of the entries of the off diagonal, which is going to be A12, A21. And it's nice to geometrically remember that pattern rather than memorizing the formula. Let's now do an example. We're going to find the determinant of our matrix 2, 3, 4, minus 5. So our determinant is the product of the entries along the main diagonal. So that's 2 times minus 5 minus the product of the entries of the off diagonal, which is 3 times 4. So this is minus 10 minus 12 gives us an answer of minus 22. Let's now learn how to calculate the determinant of a 3x3 matrix using the methods of cofactor expansion, shortcut method, and the method of row reduction. We'll start with the method of cofactor expansion. There are 6 ways to compute the determinant A using cofactor expansion. You can use cofactor expansion across the first, second, or third row. Here's the first row, here's the second row, and here's the third row. Or you can do cofactor expansion down the first, second, or third column. And we'll highlight those. There's the first column, the second column, the third column. Let's do 2 examples to see how this works. In our first example, we'll find the determinant using cofactor expansion across the first row. So that's across this row right here. We'll start by writing down the signs we'll use for the entries along the first row. We'll begin with a plus in the upper left-hand corner and alternate from there, and we'll indicate these in red. So we have a plus in the upper left, and then as we go across the top, we go plus, minus, plus. And those signs correspond to the entries that's right below them. Our determinant is the first entry in the row times the 2x2 matrix that's created when we cross out the row and column associated with that first entry. There's our first entry, so our determinant A is equal to 3 times, and what we're going to do is we're going to cross out the row and column corresponding to that, and what's left goes inside our determinant. So what's left is a minus 4, 3, 4, minus 2. And then we go up to our sign, and our next sign is negative, so it's minus 1. That's our new entry. So we'll circle our 1, and we'll cross out the row and column common to it. And then what's left goes inside our 2x2 determinant. So what's left, we have a minus 2, 5, and a 3, minus 2. And we'll repeat that process for the last entry. Oh, look at that. Our last entry is a 0, so all we have to do is plus 0, and we don't have to worry about that one. Now let's go ahead and let's compute our determinant. So this is 3. Our first 2 by 2 determinant is going to be minus 4 times minus 2 is 8, minus 4 times 3 is 12, minus our next determinant is minus 2 times minus 2, which is a 4, minus 5 times 3 is 15. So this gives us a 3 times a minus 4, minus a 4 minus 15 is a minus 11. So we end up with a minus 12 plus 11, which gives us a determinant of minus 1. In our next example, we'll find the determinant A by using a cofactor expansion down the second column. So let's highlight that column. As we did in the first example, we're going to begin with our plus minus. We always start in the upper left-hand corner. So this is plus, minus, and then whether we go left or right or down or up, that pattern continues. So this is a plus, minus. So our determinant looks like this. So we have determinant A is minus 1, and then we cross out the row or column connected with that entry. So that gives us a minus 2, 5, 3 minus 2. And then we add a minus 4. Now we're working with that entry. Cross out the row and column connected with that one. And we have a 3, 0, 5 minus 2. And then lastly, we subtract 4. We're working with that entry now. Cross out the row and column common to that, and we're left with a 3 minus 2, 0, 3. Now we just have to do the computation. So this is minus 1. We have a 4 minus 15. We have a minus 4. We have a minus 6 minus 0. And then lastly, another minus 4 and a 9 minus 0. So that gives us a 11 plus 24 minus 36, which gives us the final answer for the determinant as minus 1. Notice that we got the same answer. You always want to make sure that you get the same answer doing cofactor expansion along any row or any column. In fact, that's a nice built-in linear algebra check because you can do it 2 ways and verify that you get the same answer. Let's now go over the shortcut method. I want to emphasize with a huge star that the shortcut method is only for a 3 by 3 matrix. I'll often have students that will try to use this method for a matrix bigger than 3 by 3, but it's not going to work because the method is only intended for a 3 by 3 matrix. The way we calculate the determinant using the shortcut method is to write down the first columns of A to the right of the determinant. Let's go ahead and let's do that. Our first column is A11, A21, A31, and I'm going to push this up a little bit. Our next column is the second one, so it's A12, A22, A32. The determinant is calculated by adding the products of the entries along these diagonals, this one, and this one. And we're going to add the products of those diagonals. So I usually put a plus here, and a plus here. And then we're going to subtract off the products along the off diagonals. So that's this one, and this one, and those get a minus. So we'll put a minus below there. Let's do an example to see how this method works. In this example, we have a 3 by 3 matrix, so that's good. That means we can use the shortcut method. So here we go. Determinant A is going to be, and we're going to copy down the entries. I would suggest once you get to this point, take a quick look back to make sure you copied it down right, because that's one of the biggest ways to make a mistake when you do linear algebra is to just miscopy the original matrix. Now we're going to write down the first column and the second column to the right. So our first column is 1 minus 4, 7. Our next column is 2, 5 minus 8. And we're good to go. Let's go ahead and let's put in our diagonals. Put in those lines. And let's go ahead and let's put in our off diagonals, and then hopefully we can still read the numbers. Our determinant A then looks like this. It's going to be 1 times 5 times 9 plus 2 times 6 times 7 plus 3 times minus 4 times minus 8. Now we're going to subtract off the purple products. So this is going to be a minus 2 times minus 4 times 9 minus 1 times 6 times minus 8. And then we subtract off 3 times 5 times 7. This gives us 45 plus 84 plus 96 plus 72 plus 48 and then minus 105. When we add up all those numbers, we end up with an answer of 240. The last determinant method that we'll go over is row reduction. Row reduction involves fewer calculations than cofactor expansion, and it's primarily used for large matrices, meaning those that are 4 by 4 or higher. I've written down a procedure that I've used when I teach students this method. It has 3 steps. The first step to calculate determinant A is to reduce A to matrix B. Matrix B is a matrix that is in echelon form, which means it is an upper triangular matrix. The second step is to compute the determinant of B. The determinant of a triangular matrix is just the product of the entries along the main diagonal. So let's write down product of entries along main diagonal. Our last step is that our determinant A is going to be our changes, which I'll show you in a minute, times determinant B. There are 3 changes, and they each correspond to a row operation. And we know that there are 3 row operations. Our first change is going to be written as 1 over C, and that comes when you multiply a row of A by C. And I'll show you what that looks like when we do our example down below. Our next change is minus 1. That happens when you switch 2 rows of A. And then our last change is going to be none. And this happens when you add a multiple of one row of A to another. And I love that that one is a none, because most of the row operations that you'll do are going to be adding a multiple of one row to another row. So let's just mark these as our changes. The example that we're going to go over is a 3 by 3 matrix, but the method that we'll use is the same that you would use for a 4 by 4 or higher matrix. Just if we do a 3 by 3, it won't take quite as long. In this example, we're going to find the determinant of A using row reduction. So our first step is let's write down our original matrix. I'm going to give us a little bit more space here. So we have our original matrix. Glance back up real quick to make sure we copied that down right. Okay, we did. So the first thing that I think we need to do is we need to switch rows 1 and 2 to get a non-zero in the upper left-hand corner. I'm going to choose row 2 instead of row 3 because I see that row 2, if we divide by 3, then we're going to get a 1 in the upper left-hand corner, which is super nice. So let's indicate this by row 1 is going to switch with row 2. And then in green, let's write down what that means for our change. So our change is going to be a -1. So this matrix is going to reduce to this one. And then we're going to take our first row and we're going to divide it by 3. So we're going to say row 1 goes to row 1 divided by 3. And if we go back up at our changes, we're multiplying a row of A by C and we get 1 over C. So what we're doing is we're multiplying row A by 1/3. So 1 divided by 1/3 is going to be 3. So let's do that. So we end up with a 1, a -2, 3. And then our second and our third rows come over as they were. Now we're going to work off of this pivot, and we need to make this entry a 0. We'll take row 3 and replace it with -2 row 1 plus row 3. The change for that operation is going to be none, because we're adding a multiple of one row to another row. This gives us the following matrix. 0, and then 4 plus 6 is 10, and -6 plus 1 gives us a -5. We're now going to work off of that leading entry, and we're going to get a 0 below it. So we're going to take row 3 and replace it with -10 row 2 plus row 3. And again, that's an operation where we're adding a multiple of one row to another row, so there's no change for that one. And then finally, that gives us this matrix. -10 times 5 is -50, minus another 5 gives us a -55. And this is our matrix B. It's a matrix in echelon form, and it's also in triangular form. Our determinant A is equal to our changes times determinant B. Our changes are -1 times 3. We don't put any down for the ones that are no change. We then find determinant B, and that is equal to the product of the entries along the main diagonal. This gives us a -3 times a -55, giving us an answer of 165. We'll now go over some of the more commonly used properties of determinants. Before we begin, we're going to assume that A and B are n by n matrices. So A is n by n, B is also an n by n. And then we're going to assume that k, which appears in our first expression, is a scalar. So k is just a number. Our first property is determinant of a scalar times our matrix A. And our matrix A is n by n. So this expression is equal to k to the n times determinant of A. When I have students complete this type of a problem, it's really common to forget about the n and just pull the k out. Our next one is determinant A plus B. So determinant A plus B is not equal to the determinant of A plus the determinant of B. To compute the determinant of A plus B, you first have to add the two matrices, A and B, and then take the determinant. The next one is determinant A times B. Now this one, you can pull them apart. So this is equal to the determinant of A times the determinant of B. And our last one is our determinant of A inverse. This is equal to 1 divided by the determinant of A. Let's now do a few examples to see how to use these properties in practice. We're given two matrices, and we're going to make a note that we see that A and B are 2 by 2 matrices. We're going to use that to do our first problem. So our first problem says find determinant of 5A. This is going to be equal to 5 squared, because A is a 2 by 2 matrix, times the determinant of A. So this becomes 25. The determinant of A is the entries along the main diagonal multiplied, so minus 4, minus the entries along the off diagonal multiplied. So this is 25 times a minus 14, and that gives us a minus 350. Let's highlight this because that is determinant A. For our second problem, we want to compute determinant A times B. So this is going to be determinant A times determinant B. Determinant A we found to be minus 14. And then determinant B is going to be 1 times 2 minus a negative 2 times 6. So that's a plus 12. This is going to be minus 14 times 14, which gives us a minus 196. Let's highlight this. Just for our next problem, we won't have to repeat it. This is the value of determinant of B. Okay, so we have one left. Find the determinant of B inverse. So this is equal to 1 divided by the determinant of B. Determinant of B is 14, so this is 1 over 14. The last topic related to determinants that we'll go over is Cramer's rule. Cramer's rule is a formula used to find the solution of a system of linear equations given by AX is equal to B when A is invertible or determinant of A is not equal to 0. This will not work if your determinant of A is not equal to 0. Before we begin, let's write down what A and X are equal to. We're going to assume that A is an n by n matrix, and X is a column vector. See if we can squish it in here. X1, X2, all the way down through Xn, since A is an n by n matrix. What Cramer's rule tells us is that we can use determinants to find X1 all the way up through Xn. So instead of saying X1 through Xn, we're going to denotate one of those X's by Xj, and Xj is equal to the determinant of what we call a sub j, that we'll talk about in just a minute, divided by the determinant of a. Now let's talk about a sub j. A sub j is the matrix obtained by replacing the entries in the jth column by the entries in B. I've taught this a lot, and students always get really confused once they see that. And I say, okay, let's do an example. Let's see what this actually looks like. So that's what we're going to do. In our example, we have a system of linear equations, two unknowns. To begin, let's write down this in terms of a, x, and b. We're going to say a times x is equal to b. So our a is going to be 7, 3 minus 2, 1. Our x, we'll just remind ourselves, is x1, x2. That's what we're solving for. And then our b is our right-hand side, which is 3, 5. Now we're ready to go. We're going to solve for x1 first. So x1 is going to be the determinant of a sub 1 divided by the determinant of a. And let's see what that looks like. A sub 1 is going to be our matrix A with the first column replaced with B. So the B is going to come over in place of that first column. We have a 3, 5 instead of a 7, 3, and then a minus 2, 1. And then in the denominator, we have our A, 7, 3 minus 2, 1. And this is going to equal 3 plus 10 divided by 7 plus 6. So 13 over 13, which is equal to 1. So x1 is equal to 1. Let's highlight our denominator and note that that is our determinant A. And then we won't have to compute that again when we're calculating x2. So x2 is determinant A2 divided by determinant A. To calculate determinant of A2, we're going to take the second column and replace it with B. This gives us a 7, 3, 3, 5 divided by determinant A, which we already calculated to be 13. So we'll just plug that in. Our top determinant is going to be 35 minus 9 divided by our 13. That gives us a 26 over 13, which is equal to 2. And don't forget, when you're solving a linear system, you can always take your answers and plug them back in. So if we take 1, plug it back in, 2, plug it back in, we have 7 minus 4, which is 3. And then on our second equation, we have 3 plus 2, which is 5. So we know our answer is correct. You might want to check out the next video in this series. It's on vector spaces.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.